much for coming, and I must say, yeah, my name is Andrei, as Giovanni introduced, and I was thinking about actually suggesting a renaming at least this day from a tutorial day into really a mental marathon, Amsterdam Mental Marathon, because it's kind of, if I look at the agenda, there's so many cool topics, and it's really, I was thinking like, wow, you really have to concentrate actually 8 hours or so on a very diverse set of things, and I'm lucky enough to be still in the first part of it. But then I thought, well, let's not kind of cannibalize that, and also I made my talk also with this in mind, so that hopefully we're going to cover some useful stuff, but not really requiring yet another half an hour of so deep concentration. So about myself, well, as Giovanni quickly introduced, I work at PySpark, and this one actually, it's a funny engagement profile, is we work a lot with Microsoft and the Microsoft communities, and they run their own sort of smart algorithms that automatically detect sort of the profiles of the experts, and at some point that's how I was kind of tagged, and I actually found that this is probably the most relevant stuff. I was never able to explain like what I'm exactly doing, because I've been coming from high performance computing, from neural networks as from my education, then I switched more into really development part, and into commercial, then I got back into actually to the academia, did my PhD, and then switched back again to the industry, as they call it. So, but essentially I work with data on on scale. That's how I would put it myself. And our journey today is, actually, I'm going to start a bit with the context and the motivation, because I do think still my talk is probably not really on the same level of details as that might usually happen here. So I have to introduce a bit of the concept and the things, because I don't think that everyone is working with this technology. So I'm going to use kind of a slideware and a PowerPoint for this mainly. And then once we move forward, we're going to really start building some stuff. And then I'm going to use basically Flipboard and the web browser only. So I don't have any local setup instead of PowerPoint. The only thing is I need the internet. And yeah, perhaps we can just collectively actually develop the scenarios that support my conversation. So the context is basically about real-time streaming processes. And what is real-time streaming processes? Well, it's a pretty broad topic, but in essence, and this is where my personal focus is, as the focus is basically in IoT. And IoT, of course, well, as I say, for me is not a device business, it's not a things business, but it's a data business. So IoT itself, it generates a lot of data with a very interesting also nature, which has also streaming nature, and those kind of other properties, like there's a lot of broken data because you have to deal with the real stuff. And there is, of course, a number of scenarios, which I don't think I need to go really into details, but from all kinds of monitoring scenarios up to more sophisticated, kind of asset tracking, routing, up to the actually all kinds of pricing analysis and stuff like that. Usually, I think reference case outside IoT is used like fraud detection on the running transactions. This kind of a streaming data, basically where you have like a continuous flow of data, and you really have to work on it in at least semi-real-time or close to real-time, because it doesn't have that historical nature, right? I mean, if you have transactions, you really have to detect it as it comes, and not somewhat one day after. So that is a bit of a context around streaming data and its nature and its applications. So actually, I'm gonna use a couple of building blocks. I don't want to talk that much about, you know, Azure and cloud and stuff like that. I think some of you know, you know, what it is and the principles behind that. I'm gonna jump straight away into the, I call the building blocks, which I'm gonna use to actually motivate and illustrate actually end-to-end, well, a solution how, you know, the data can be, you know, ingested and then picked for further analysis. So, and Azure Event Hubs is one of those building blocks that I'm gonna actually use. So, Event Hubs is built and designed to basically facilitate the ingestion of the data on a high throughput. You know, think about megabytes per second of the input data. It is, of course, scalable. It has certain features like time retention buffer, so you can keep the messages inside the kind of the service bus, if you will, for a certain amount of time. So it's not really kind of a fire and forget model. And of course, it's scalable, so it's completely PaaS offering, is called basically. You don't have to manage any kind of infrastructure or virtual machines and stuff like that. So you just get this building block, and you know you can start actually ingesting your data. It has actually one, in a way, limitation on one focus. It's not on the same principle. It's not really built exactly on the same principle as positioning as Kafka, which is probably many of you know. So it has limits on the message size. So it's not really a general purpose kind of you know data streaming hub. It's really optimized for high throughput, but you can't send you know 40 megabytes of messages into it. So it's actually limited to a few hundred kilobytes. So if you look at, I'm gonna quickly go over it. In essence, you know, you have this kind of an IoT world and the data world or big data world, and the event hubs is just in the middle. So it's really an ingestion mechanism with kind of where you can push data from different kinds of you know, gateways or devices or whatever, and it's also you know, facilitates the consumption on a large scale of the data to further, you know, analysis and storage and processing, whatever you do it. So it's really kind of a front end which sits in between the, you know, the IoT data and really the data analytics, which I think most of us actually in. A bit of an architecture, well, it has this notion of partitioning, which some of you might know from like, you know, NoSQL databases, where you can basically kind of control how the data is partitioned and split. It supports somewhat also the scalability, but basically you can control by providing certain keys, and then based on that key, your data is going to be split into different partitions, and each partition is a kind of a queue where, you know, the data comes, and then the data consumed. You know, of course, the event producers. It supports two major protocol, HTTP and AMQP. So, you know, AMQP is basically as a de facto these days is a standard protocol for all kinds of messaging. But when it comes to the IoT, not all devices support, for example, AMQP for various reasons. And also the difference is AMQP is you get live connection, so it's stateful, and HTTP is just you have to make a connection all the time. You know, it's request response based. So if you have like really high throughput within a certain amount of time, then you probably use AMQP, connect to the event hub, and then start pushing the data, where HTTP of course needs time, and there is some overhead to make the connection all the time. And of course then this is also an interesting concept of the event receiver. So event receiver consumes the data through a so-called consumer group. And consumer group, it's actually, I find it's quite an interesting principle, because it's basically a logical view on over event hub. That means that basically different consumers can have their own independent, isolated view on the data. So basically the advice is consumer group is per receiver. So if you have one application, that's one consumer group. Second application, it's a second consumer group, so that they don't interfere with each other way. So that is a bit of on the receiving side. And to summarize, so the throughput is, they have this throughput unit, so one block is actually 2 megabyte on read and 1 megabyte on write, but then it's scalable. You can increase those throughput units, and it has this also interesting notion which is based off CompP, client-side cursors. We're gonna come to this notion a bit later, because cursor is the one that is actually the principle that allows you to build the consumption part, right? Because you have a streaming data, and cursor, that's always like a moving slice where you actually consume this data. So that is a bit of about event hubs. The second building blocks is called Azure Databricks. I don't know how many of you are actually into sort of Spark, perhaps Databricks business. Not that many actually. Okay, so that's what I envisioned. So actually, then before I jump into the Azure Databricks, I just make a quick, very brief, introduction or snapshot about Apache Spark, because actually Azure Databricks, it's an offering that is based on Apache Spark, and in essence, all the stuff that I'm going to talk about is not per se Databricks specific. It can be implemented in a open source edition of Apache Spark. So I'm going to just use the Azure Databricks for various reasons, including that I'm actually, over the last couple of years, I've never done anything on my local machine. So it's kind of, it's everything in the cloud. They need a browser and the internet, and as soon as the data is in the cloud, then I'm not really working that much with the managing Spark clusters, but it is possible to build. So Apache Spark, well, it's a sort of really, they try to position as like a unified framework for data analytics. It basically has the core engine, which is by default based on sort of distributed computations. It considers, it has some basic data structures which are by default distributed. So whatever data you feed in those data structures, they get partitioned across the machines and the clusters, and then the computations happen. So on top of that core, they have different schedulers. So this is where actually the jobs get executed. And then on top of that core engine, basically those are the major components. So Spark SQL, this is actually like a SQL dialect for actually, well, what you would expect from SQL, running in interactive queries. There is a library called Spark MLlib, which is actually, it has some machine learning algorithms implemented on top of that distributed backend, which is by itself a super non-trivial task. And those who are really deep into really machine learning, not everything is parallelizable and distributable, so it is somewhat, from my perspective, well, limited and constrained for the reason that, it has to run on a large scale on a distribution. Spark streaming, this is what we're going to talk about today. That's the part and the API for streaming processing, and it also has some graph API where you can work on a graph-related data. So basically, if you look at this, it kind of sounds very cool, because there is more or less everything within one framework. Of course, it has support for all kinds of also deep learning frameworks, for example, but that is something already which then needs to be done custom. And on top of it, and that's not really a default Spark package. So that is a bit about Spark. So as I said, the architecture, so it has this kind of a driver worker concept, basically masters slaves in a way, where driver is basically like the entry point for your code, for your program, where it is executed, and then everything gets distributed actually and gets executed on the worker nodes, and then those worker nodes, you know, they actually access the different data sources and do all kinds of also like caching to try to localize and optimize the data so that, you know, the data gets cached on the local workers in the optimal way, and those kind of things. It supports, you know, HDFS, not only HDFS, but, you know, all different kind of data sources, GDBC, all kinds of databases, of course S3, different Azure storages, and it has, of course, the default cloud, so to say, way is it's available in all public clouds on as a set of virtual machines, and I'm now talking about just the default Spark offering. So the PySpark, so what is actually the relation between the PySpark and Spark? I find it's quite important. So usually you come to this diagram, and I put this references and more details about actually the internals. So Spark is written in Scala actually, so it's a GVM-based environment. However, it supports as a kind of client or as a front end, you can use R, Python, and of course Java, Scala. So we're going to talk about a Python stream which is called PySpark, and actually how it works is that there is actually a way where a GVM forks Python processes, and then it communicates with the Python processes via pipes, which is like an inter-process communication. So one can say that, of course, the most optimized way of using Spark is still Scala or Java because it's written in Java. So here you get some, of course, overhead within this inter-process communication, but it's not really a large overhead comparing to, you know, the duration of the whole computations that are taking. But in essence, it's a somewhat foreign process which is then supported per each worker. So that is actually about Spark. Now I just want to actually go into the Azure Databricks and what it is, and well, why I find it's actually it's really a very useful building block or component that is available, and I'm gonna now switch into the browser, and actually I think it would be just best if we follow my browser session, because of course, well, probably some of you could have get an Azure account, because actually everyone can get Azure for free with $150 credit as a sort of as a trial. But I think it's going to take too much time if we start to kind of organizing this. However, all this stuff that I'm doing is going to be completely reproducible, so I can export all the code and configuration that I'm using, so you can try or replay this yourself. So actually this is like basically Azure portal. So I'm logged in with my account, and basically I have this resource group notion. So resource group is like a logical way of group different resources, and here you can see that I have two resources that I pre-created. One is the event hub, and second one is Azure Databricks services. So if I go to Azure Databricks, it has that notion of workspace. So I'm launching the Azure Databricks workspace, and now let's go a bit over what it actually is. So in essence, yeah, sure. That's good. Is that? Yeah, yeah, okay. Yeah, thanks. So basically, this is what they call the a unified workspace. So the workspace is organized per each user. So as a user, I get my folder, and then within this folder, I can, you know, create a new notebook, give it default language where I want to use with that notebook, and then associate that notebook to the cluster. So it's kind of it's a very similar concept, of course, very much inspired by what you have in a Jupyter. However, that's a bit more coupled with the whole way of how Databricks is organized. So if I create a new notebook, then I get my basically notebook where which is attached to the running cluster, and there I can start basically writing the code. Important stuff is, so if you go into the cluster, this is actually a Spark cluster, which is, I think, one of the most useful feature of Azure Databricks is, you don't need to manage the cluster yourself. Here I can do a cluster name. I can pick the runtime, so what kind of Spark version do I need, which Python version do I need. I can pick the different sizes of the computing behind my driver, and I can also specify the size of the actually computing behind my worker, right? And here you get basically different options, and those are actually the ones that Microsoft has as just as a VM, and there you can even, there is a GPU accelerated machines coming. So based on your expected workload and the scale that you need, of course, you can adjust the type of the sizing that you need. I'm gonna go for just a default one, for 14 gigabyte of memory for cores, and then here is also another interesting feature. It supports auto-scaling, so I can specify the minimum amount of worker nodes and the maximum amount of worker nodes, and then there is some heuristic that when I begin my computation, it starts with the minimum, but then if there is a pressure on a memory or CPU, then it starts auto-scaling cluster as the computation happens. So that. And then the third one, which is quite important from the really usage perspective and operation perspective, is this one. You can specify the auto termination if the cluster is not in use. So if there are no jobs are running, and then I can specify half an hour or 10 minutes or so, from 10 minutes to 2 hours. If it's not in use, then the cluster gets automatically terminated. So you don't have to pay for it, which is quite important in the cloud. And this is, I think, something that is like, well, it is a strong, how should I say it, a selling point, then can your cluster also do this? It's quite useful. So I can specify all kinds of Spark config and stuff like that. So I pre-created already the cluster. Yeah, so Data Factory can invoke notebooks. That's out of the box right now. It's also sort of, it used to be in the beta stuff. The jobs part, it is actually here a native feature of the Databricks itself. So here to the clusters, in the clusters, you have two types of clusters. You have the interactive clusters. This is where you work sort of experimenting, exploring the data. But then if we go to the notebook side, here, and this is, I find this is really killing for the practical stuff, and especially from the kind of transition from, you know, like data science, data engineering into really like any kind of production operations, all this scheduling stuff, you know, that's something that is actually very non-trivial thing to build. Then you need to kind of CI/CD or some kind of deployment into the new cluster. So here you can just schedule the job and really use, basically cron syntax or just manually specify, and then it's gonna, once it runs, it's gonna create the job clusters. Or from here, I can also do it backwards. I can create a new job. I can specify the notebook, or it can still very much work with, binaries like jars. And then I can specify the type of cluster, right? So I can configure the cluster, and also I can configure the schedule. But also an interesting part is this one, which is also you get it kind of for free. But it can, for example, do an alert if the job has failed. Then it can send an email notification and stuff like that, which is like otherwise needs to be built. So the job part, at least, well, we use this quite heavily, and we kind of separate the notebooks. If you talk about data engineering, which is Data Factory is, so if there is some data transformation in the notebook and not the job, then it can be triggered from the Data Factory. But if you see a Data Factory more as an end-to-end orchestrator, which does, first data cleaning, data engineering part, then, for example, some scoring or some publishing, then it can still trigger the notebooks that do, scoring, for example. But we use it more for. So the jobs, let's say, what you would usually see is just a Databricks native part. So we only trigger really the data processing, data cleaning part from this one. Actually, there is it has an API where you can, of course, do. It has REST API where you can up to submit the jobs, create jobs. So all that functionality is actually also replicated with the REST API. So this is like, I came from the experience where you manage to really be productive, so to say, and to work with data. I kind of managed to skip this moment where you can use with data on your local machine. If I work with like satellite image, that's how I started kind of working with data. Satellite image, the original one that for example then gets down to Google Earth. The size of it is 450 megabytes. So one image where you have the whole range, then ultra range in there, etc. So you have to think how do you organize it, and the only way to organize, well, then you need to build some kind of cluster, right, with all kinds of MPIs and for example MPI or other things, which is then you spend 80% of effort, building, figuring out the infrastructure, and this is like really a matter of minutes, which is, to me, I'm still very, very excited about that whole like cloud. It's not something that is like very far, but it has this benefits for what we do and for what I do. So this cluster, the job part, Of course, the workspace, there are a lot of other things which are also quite useful. There is, of course, the admin console where you can also do access control, who can do what, and etc. So it's kind of built for really collaborative work, and of course, not everyone, for example, is allowed to spin off in new clusters. So that is a bit of data Azure Databricks part which I wanted to cover. Of course, there is also, I have pre-configured the event hub, but there is nothing really special here. I actually use it for various purposes, but you have, that's the stuff that we talked about. You can create different consumer groups. There is one by default. Then you can get some telemetry, some monitoring. What's going on? Well, nothing is going on. Some throughput stuff. Important is then is this one. We're gonna use it. Shared access policy is that basically with the policy you can organize more access perspective. So that policy means that the ones who use these keys, they can manage, they can send the messages, and they can also listen to this. So I just made it a full access, and this is then you get the connection string for both for clients and suppliers, so to say. So this is a bit of the Azure part. Is there any questions so far around this one? Yeah.
Hi.
Yeah.
I think I have a question about those clusters of
Yeah.
that you said you pay when you use it, but I see also problem with the performance of the cluster. It's not only up and down. It's like if the performance drops, it's also not good. Have Azure have any control over this? About performance monitoring?
Oh, that's good. That's a good question, actually. Thanks. Of course, here in the cluster, you have two things. You have still the native Spark interface. So here I can go to Spark UI, and well, the usual things that you would execute, what you expect from optimizing and tweaking Spark, it's still there. It's not really any kind of customized or patched Spark. You get the default interface, and you can access to all kinds of Spark provided metrics. To first of all, to get the details into Spark, right? So that is level one. The level two, of course, probably you're talking about the underlying, VMs and computing side. But those VMs, they are nowhat different than the default. If you, for example, want to install, Linux, you go to the portal, say, I just want to plain VM, and then there are going to be a lot of sizes. And of course, those VMs, they have different characteristics, like they have different generations of CPU. The storage is behind is different. You get an SSD storage and the regular storage, those kind of things. But this is not really specific to this part. So you can see your Spark utilization. And of course, what is the optimal configuration of this? This is the question which is like, there is not really a straightforward answer to this. You need to investigate, what is actually the optimum. They have some categorization, like for example, storage optimized or this compute optimized, this FH, they use the latest generation of Intel processors. But of course, then they're more expensive. This is kind of the balance that you need to make. Does that answer the question or no? What are they exactly looking for?
You run the job normally take 1 hour, but the performance down take 2 hours, and then you don't want it to take 2 hours. Is there something that Azure can do to switch between different clusters when it notices a performance drop? Can it like prioritize some important jobs as well?
Yeah, it has, no, but this is all still, it's a Spark specific things, right? I'm not seeing in what way it's Azure specific. It has some scheduling ways, which is again Spark specific. So if your job runs 1 hour on the same data set, I can't see why it's going to run 2 hours on the same cluster size on the same data set. Of course, if you have 10 other jobs running at the same time that are taking resources, this is any kind of framework has that issue. I mean, from MPI to just a default Spark, right? So optimizing for this is a pure, and it's probably a separate topic, I think, because I'm not quite sure, yeah, how that can be answered sort of in a very concise.
You still use the normal Spark metrics thing.
Of course, yes.
You could send stuff to something like Grafana or something and monitor it from there.
Yeah, you.
Next metrics are still available.
I mean, you get. I mean, this is the view of sort of visual stuff, but this also information you can also consume and automate. But there is nothing I would say that the Databricks specifically adds on top of this. Of course, they optimize the engine, but that one, for us it's given, and at this point you have really a very detailed access to the usual Spark one, and when it's running, then of course it's changing and you see what's going on. But then, yeah, of course you can put it somewhere else for more detailed analysis and stuff like that. So that would be my probably ultimate answer. So any other remarks at this point?
Can you create dependencies between jobs?
Yes, you can actually, in there the concept is, they call it notebook driven workflows or something. Basically there is a way you create like an entry point, which is a notebook, and then the only thing that notebook does is invoking the other notebooks. So you compose your jobs, because the entity is a notebook. It still runs in notebook. And there you can also, for example, programmatically specify like the timeout, the exception handling and stuff like that. So you have a Python like a main function which invokes the sub flows, which are notebooks themselves, and then the way how you handle it, what kind of timeouts, what do you do with exceptions, you can control it yourself. So it's not really like to be, it's not really a replacement, I think, for things like Airflow, Databricks. So it's not really from the orchestrating is not that powerful, and it's not supposed to be. But if you have more, your code is somehow composed in different notebooks, then you're going to have a main function that just invokes them sequentially, and doesn't make sense to invoke the second one if the first one has failed. But it's not really a replacement for this, for the kind of an end-to-end, orchestration frameworks from my perspective. Even though, of course, you can build it in because it's just Python. So basically, this is like about this. So now let's jump into this part, and this is where I think we're gonna slowly move from the slides into actually coding, because I have cluster, I have notebooks, so you can start actually doing. Also, just want to probably quickly make some reference. So there is this notion which is called continuous applications, and this is the notion which is very much promoted by Databricks themselves. And Databricks, that's the company actually that is founded by the original Spark creators, and they're kind of still major contributors into open source Spark itself. But also they run this Databricks as a company, and then they have also AWS kind of offering, and Azure Databricks. That's a close collaboration between Microsoft and Databricks to make it really the default Microsoft offering. Just about what Databricks is it, because I'm referring to the Databricks. So they promote this notion of continuous application, and continuous application is basically when you look at, especially from the streaming perspective, like most of the use cases, they are not really actually streaming only. So if you look at this side, like input, then you have some computation, and then you put it somewhere into some output. That's usually actually not the case, and most frequently not at all. So the obvious reason why it is not like this, because especially if you talk about the IoT, the size of message is very critical. So from those devices, you get really only the, let's say, the sensor-specific data, which is optimized or should be optimized for size, because you don't want to use your network bandwidth. So where the type of data that you get here is really very specific to a device, which might get some kind of device ID or something like that. But as for example, as a data scientist, well, you need to have some enriched data set, right? So you can't really work with device IDs and their location, because it barely means nothing and not useful. So what happens immediately then to this, you need actually join or enrich your streaming data with data from your CRM systems or other catalogs. What does that device mean? Does that device mean, for example, or other things? So this kind of enriching the streaming data, this is one of the obvious things that is coming into mind. And then on top of this enriched data, you of course have different perspectives, right? As a more exploration perspective, which is to call ad hoc queries. You can do, of course, still send some the output, the processed output somewhere, and think that's the kind of a tunnel that does that. Or, and this is quite important, this is the fundamental principle that actually Spark is positioned to actually be different among the other streaming frameworks. The principle is here is that basically if you have streaming data, or let's say it in simple words, the certain piece of the streaming data which is coming, for example, over the last 10 minutes, the result of this invocation of some code on top of that piece of streaming data, it should be consistent with as you would be executing just a static batch job on top of this data, which is kind of sounds very naturally and very logical, but that is not really a trivial requirement. What happens is, let's say, if the data it needs to be analyzed in real time, then there is some streaming framework is being used, and if there is some report, for example, has to be produced on top of the data, then the data is stored and some other mechanism is used to work on the same data set. And so what happens is the most often they can produce different results, because you don't work with the LDL data, things are failing, and etc. So having that consistency, this is quite important, and this is actually very natural to look at this. So as I said, consistency. The other one is fault tolerance. If you think about it, the distributed streaming is actually quite challenging task, because if you build such a framework, things are failing, or even your nodes in the cluster are failing. So if you start kind of, if this is your, I'm gonna slowly switch also to the flipboard. Let me know, if this is your input, and then if you have this kind of, map reduce, more kind of stuff, where you have different pieces kind of coming together, right? But first you split the data, you partition it, you put one piece here, one piece here, and then you kind of join the results back. So what happens if that guy fails. This is like the obvious thing. You really need to guarantee here because we are really talking about the streaming data, which is quite important. It has this, time order perspective. So having that fault tolerance is extremely important. Otherwise, you might still get the data, and this is where the third one is coming. The data sometimes might come, this is so-called out of order. So when the time when the data got produced for some reason, for example, there was no internet connection. So the data has a timestamp, but then it was sent in a different moment of time. So you don't want to deal with those things. And actually Spark streaming deals with this. It kind of guarantees that out of order data, the data that was delivered here later, at the processing side, we can still expect is to be, a continuous stream. So those are the things that actually makes Spark quite an interesting or actually quite useful, and it's being used a lot. I think 60% of Spark use cases, at least that's what I read, are actually streaming data because of those features. So I think I'm not going to go too much into this stuff, but actually the principle is this one. The data stream data is basically like an unbounded table, so you should see it. The data stream is considered basically as a table where the rows are appended. That's the basic principle. And then once the data is always appended, so once you consider everything as a table where the rows, the incoming data gets continuously appended, then you can actually work on the streaming data the same way as you would be working on a batch static data. And of course, well, with the time, then things get appended, and so I'm not think this time series. Well, it's obvious, and this is logical what you would explain, right? So if you look at the time, the input table grows, but then the output gets taken. Is basically first in, first out kind of principle, but implemented on a large, on a distributed manner. So it has a lot of built-in sources. I'm going to use Azure Data, Azure Event Hubs as a source, and now we're going to switch into the completely into the notebook. So actually, how much time do I have? I have half an hour, right? Yes. So I kind of created this model or scenario that I want to use. So imagine we have a parking garage with a lot of parking space, and then each parking place is monitored with a sensor. So, and that sensor is streaming the data. And then I came up with this model. What is in this data? Well, there is a license plate, the spot ID, so which spot is taken. Of course, the timestamp when it happened, and the type of event or operation as a car entering or leaving. So we have sensors a bit more smarter than this one. And so that is the model which I want to kind of illustrate how can we really work in such kind of setup with Azure Databricks and combined with Event Hubs. So what I'm going to do right now, of course, well, I don't have the test parking garage. So what I've done is I have the emulator which really streams the data in this model. So in essence, what happens is, wait a moment. It's not this, it's this one. So when the car enters, it kind of generates the event with those data set, and then I have some emulation that the car remains parked between 0 and half an hour, and then it leaves, and then when it leaves, the event gets generated. So that is a bit of my my model. So I'm gonna run this this emulator to see, you know, on one side, and on the other side, I'm gonna switch to this. So basically, I prepared some kind of a boilerplate in essence. So first part is, of course, the connection to the Event Hub. So as you can see, Event Hub is a default format that is now supported. So that support was built by Microsoft, and then this connection string I took from my Event Hub settings, and this guy is now, you know, streaming the events. If I stop this and I start running the stuff. So actually, as you can see here, and this is in the cool stuff about using notebooks, it derives a schema of the data frame that represents my stream. And within this stream, you can see actually the body. The body is quite important because actually this is the message itself that is being sent. And these parts are the ones are specific to Event Hub, you know, like offset, sequence number, enqueue time, etc. So this one is quite important to work with the stream data, because offset is actually the position of the message in the queue. So without actually getting the data, I get already the schema of the of my stream. So if I'm gonna now do this, so it gets some initialization, and let's see. I can have some, you know, here some actually way of seeing, you know, input rate versus processing rate. Well, of course, I'm not streaming that high throughput, so it's kind of very much the same. And then I also see the batch duration, because what happens is that the streaming data, as how it works, is it's still being converted in the little batches that are being moved over the incoming data. And an offset, that is the position inside. I also have raw data. I can see, well, how many records per second, and etc. And it is running. So this is a continuous. So, and this is here. I can see actually my data, the one that is being streamed here. I can see actually the real data. So it's not that much useful at the moment, because, well, we obviously are interested in the body. But body, so it sends as AMQP. It's a binary protocol. It's binary serialized UTF-8 JSON message. So the original message is JSON encoded, but of course it got serialized. So if I can cancel this for the moment, but this is like the first actually very interesting principle, that, you know, you get immediately an abstraction over something that is actually quite complicated, but you get it in a way that it's a structure, it's a data frame. It's exactly the same structure as you would get it by working with data from database or data lake, and it gets a schema, and you can actually have all those benefits available. So what we're going to do here is, of course, this data, well, it needs to be converted. And what happens is, here is basically we need to just do this usual thing, which I guess a lot of data engineers, or most of us, do all kinds of casting and conversions to the data types that we would like to use, right? So the offset is actually, it's a long, so the enqueue time, it's a timestamp. The body, we will get it back to the string. And then this one, we select just 4 fields, because we are not interested with the rest. So this is like basically a typical Python thing to work with, to really cast and do all kinds of type conversion. Interesting thing is here you can see this with column, and then cast, and then you produce another data structure, because the data frames, they are immutable. So you can't just say rename the column or replace the type. You have to do a transformation which maps the original one to the new one and then do select. So that is basically why it's a bit verbose comparing to if you would have like in pandas you can rename, I think, things in place. And this is like the typical thing. When I started with Spark after pandas, like how do I do this? And you can't rename because it's immutable. So you have to think in transformations. But this is what actually happens. So I run this. Again, so input stream, we kind of forgot already that the data is actually being streamed. So I've got my new schema, and well, I can also display it. That's my personal way of doing. When I do some transformation, then display and see kind of what happens. Well, that's already way more useful because here we can see we can convert our binaries to a string, which is then represents the my JSON, right? That is supposed to be streamed by device. So not to keep that running, I did some, well, also license plate generator, but it doesn't produce really something that probably Dutch would recognize, but anyway, I think it's not that important. So this is important, the operations. As you can see, some cars are leaving, some cars are coming. This is the timestamp. If you look at this one, is because I emulate the time, and some time is actually already in the future because in my emulator I add like half an hour that the car was parked, but reality is, of course, well, we did it in a couple of seconds. So this is good, right? So far, so good. Body, and we've got the body. So then, of course, we want to convert it into something that we can actually work with. And for this part, there is a way in Spark to define actually schemas of the type. So we define, because if we look at the JSON here, and we know what kind of input is, we can specify the schema. So the schema converts the basically string or any kind of unstructured data. It can be actually quite complex type on all kinds of nesting. It converts into really a tabular basically view. So we specify the schema, and it also constrains if the data is not compliant with the schema, then what happens is, for example, if I would not specify one of the fields, it would just skip it. So I would only get the part that I specified. So we've got this. Now what are we going to do here is, let's say we do cars. So we've got our messages, right? And this is still streaming. What we want is we want to convert from JSON, the column body from JSON into applying this schema. And again, we need to make it an alias called data or something, because otherwise the new column is going to be generated. So it's not in place conversion, it's a transformation. So each selection is a transformation. We make the alias and then do this trick. We do it select again. With this dot star, it allows us to actually explore all the fields, right? So we've got at this point the data column, and then we want to really select those columns. So we've got the data frame that actually, now here we go. So at this point, actually, as a matter of fact, it's just, yeah, I do it in the different cells. That's a bit of a way I can do, and then I can also, execute it and to see. And at this point, as you can see, it's a running still stuff, so it's a continuously running stuff, but we've got an abstraction that is basically the same data frame as we would be using static data, right? And we've got stuff, columns already expanded by using this from JSON method that's a built-in Spark. There's nothing and that I've built here, and the schema that I was just specifying. So basically, this is like the basic principles that emulate, you know, this part. And this is what called, you know, structured streaming. That's why it's called structured, because it actually relies on some backend, and then we are really forced to specify this. And then at this point, yeah, we've got just a regular data set, which is you see it running, and it uses append mechanism by default. So it's kind of a lazy data structure, because obviously as soon as we start using it, if we, for example, want to do this, which is another interesting feature of this notebook, you get this different visualizations by default. And here we can, for example, visualize. This is like this. You still. Do you still hear me? Yeah? Thanks. So as you can see here, we can visualize this, our streaming data, picking some operations. I call this ops. So ops is 0 is entrance, and 1 is leaving. So we can still see, you know, in the real time, this also gets updated. So how many different cars are coming and leaving. So, you know, which is like here, it has this batch interval, right? So it's really well, not really in that sense real time, as people would say, but it's quite low latency still. You know, 5-second batch, and we get this updated. So this is already like, you know, to build that use case, having, in my scenario, what is only missing is the real, you know, devices and sensors, because I have that emulator. But if there will be to come this to like, you know, basically in half an hour, I think this is a very productive way of doing things, and especially all kinds of, you know, prototypes, stuff like that. So at this point, of course, we can zoom and generate all kinds of scenarios where we would probably we can imagine with this, but then at the end of the day, it would be still along the lines where we would be applying some functions, you know, on top of this. So I think for this, for the streaming part, this is what I wanted to show at this point. And then, of course, the interesting part, what begins is, you know, you have this more interactive part. So one scenario is really working with the real-time data. For example, I don't know, alerting something is some system if the garage is full, right? There you don't need the historical data. You really need to put some detector on top of the data that you get. However, there is a lot of useful stuff can be done with this data from the, you know, more data science perspective and for advanced analytic perspective, right? So we can zoom into, for example, what's the average duration that car stays, or if we know some license plates, some insight about this. So there is a lot of stuff that can be done based on the historical data, and actually now I want to show how to kind of facilitate this. And yeah,
the mic. The back of the mic was off, so I just want to check.
Yeah, sure. Oh,
Yeah.
that was the wrong way.
Yeah, it looks like it. So.
Oh,
There you go.
oh yeah. But now it's still something. Well, this is
Such a good
this
thing.
is symmetric. I think now it's like this.
Yes.
Yeah. Right. This one. Yeah. Yes? Good. So basically, this is, as I said, the streaming data, and there is a trick to convert this streaming data into something which can be considered as basically historical data. So here what we're going to use, the same thing. So we've got our messages, which is an abstraction, but then we can start writing this write stream. This is actually the output, so this so-called the output sync. So each, I think it's still something weird. Each of the input one also has the write stream. So that allows to write into all kinds of outputs, including more relational databases and other things. And then we can do the streak basically write into memory, and give it a name, and give it a mode. So it creates a in-memory stream, which then basically can be considered as a sort of as a temporary persistent storage for debugging, and kind of doing all kinds of more static data stuff. Because otherwise, I would need to write this data then somewhere into a database or other things, which it's probably going to take even more time to do. So if I do it like this, we initialize this memory stuff, and I'm gonna kill this one. So now we started basically that conversion from our messages, which is already a structured way, into the memory output, which we gave it the name car, and then at this point we can actually start running SQL-like queries. You see, on top of this car, which is already this one. So we compose actually. it's really, if you think about it, this is where it already becomes quite complex. It's, kind of composing. If like functional programming people would say, like composing streams, that is something that goes like, you really have to be in the championship league kind of to really develop this, because and especially in a distributed fashion. So that's another thing that makes me quite actually excited about this kind of composition. And really, it's so simple abstraction. You get data frame and the stream. That's the thing, and the transformation. And then you kind of compose things around, and you don't even feel that is non-static data. So what I also want to show you is some things that are not actually supported, even though it would be really cool to have them. Like I was asking myself, what could you do with that data? And the obvious thing that comes to my mind is detecting the duration of stay, right? And to do this duration of stay, it's also not trivial. You need to have this so-called window primitive, which basically allows you to partition your data. Because actually what we need to do is we need to sort it by ops and the license plate, right, in a decreasing order, and then do a difference between current row and the next one. That would give us a duration state, right? So if you have time, we need to resort it. And that is, if you think about it, in a distributed data frame, because you can't universally and navigate as you would do it in a sort of imperative language. So that is actually the way to do it. So what do you do? What you do is you actually still need to create a new column that represents the difference, and basically then what we are trying to say is you have this this leg function with this one, which actually does the whole tree on such kind of data sets. So what it does, this one attribute, it allows to actually make an operation over, not over the columns, but over the rows. So what it says is, it's very declarative, right? So I need to cast it to integers, and then do the minus the current row versus the one beyond. And this is typically what would do the trick. However, here the interesting part is we need then to, so partition-wise, is you can see it as like a group, it's like a grouping, right? But this one, if I actually execute it, is gonna say that the partitioning is only supported on a time series. So if this column is time, which is kind of obvious if you think about it, especially in terms of this out of order data. So you're not that flexible to do such sophisticated things on the streaming data. But I just wanted to keep this in a notebook so that actually I think we could. I now replaces this. Usually, I think people don't talk explicitly about things that are kind of failing. Even though at this point it's interesting, it derives the new structure. But this, as soon as it is lazy, so at this point I was actually still quite happy because I thought, wow, I'm gonna do it. But this is where it makes it, it converts, it really executed from lazy, just an abstract data structure which has a structure but no data, and it really starts, it really needs to, and here is what it says. This is actually exception if you go to Spark code, then it checks the types of these ones and then throws this exception. So, you know, still there are some ways, and actually if you think about it, probably the duration you would need to see it more from the historical perspective, but sometimes those limitations are in place. Also, what is actually possible is, I was showing it with the memory, it's possible to, of course, write it in a more, in a persistent storage. So here I have the, can delete this one. Why am I started popping up? So I still relate to my input stream, to the really original ones that keeps still track of, and I'm going to shut it down because, and then again, this is just a different syntax. Actually, is not a Python native, but you can invoke the SQL primitives on the Python data structures. So by using this, and then of course we always need to do this conversion because I'm going back to the input stream, right, to the original one where the body is still a binary, and then again applying the same trick with the schema transformation, and this way I get my another type of actually I think I should do it because then it gets nested stuff, and that should be yeah. So that flattens the again the streak where you go, you know, like if you do it without this, right? You get this field that is a structure by itself, and then it gets nested. But we would like most likely to you know, work with just a flat. So I've got that my archive data, and then actually I can write to more persistent output location. In that case, I use Databricks comes with a local file system where, you know, I can use it as a local file system. And this is actually also interesting, checkpoint location. So this is what you would be using more for production setup. So checkpoint location, it's you know, because those streams, if you run it in production, well, things fail or other things, bad things happen, so that the stream gets interrupted. So the checkpoint location, it's like from certain within a certain time frame, it commits the data that is in the stream and saves it to a permanent storage, so that you can reconstruct. So if something fails, you rerun the same query in the future. It's gonna, pull the committed part from this checkpoint location and then continue with the live one. So this is another interesting moment where you can basically replay the string, replay the stream. This is how they call it, which is a principle that is also behind this this framework. And checkpoint location, well, it's a storage, and this one is then I put this my test data, and then I can kind of run this. I'm still quite surprised that nothing, it all kind of works in one side and keeps running. And then if I look at this, for example, there is no really good way to navigate, but I can look at this. It's kind of a file browser, if you will. Of course, it created this, and it stores, it actually serializes. If you can see here, it uses Parquet format, which is way more efficient, of course, and then it serializes the parts of the data in the Parquet format, or it can be whatever format, but when it comes to more data lake type of things, that's what's more optimal than all kinds of CSV. So you can see here that, the check parts, it has more complicated stuff, but my test data, this is the stuff that is where I actually write it into the output. So that one is also working. So I got back. I created this upfront also consume part. So as soon as I stored this, so someone else, imagine like data scientists, can actually already start using this data. And this is very simple. So I can just do this, and you see it reconstructed. So I use it, usually you use the folder, and then it depends, of course, all the Parquet parts, and you do it like this. So that is, you can already start working on some slices of historical data, which is stored in the, well, that's not really permanent, because if I restart the cluster, then it's gone, but it can be all kinds of permanent data. So that is like really a permanent storage, sort of interactive part. What I also was planning to show is something that is called stream joins, which is a relatively new feature. So you can actually do joins on two on two streams. When you have, like, I came up with this idea where you, for example, have one stream that I have, and the other stream can be like some payments mechanism where some license plates, they do some like monthly ticket or something. So that stream would actually generate this kind of a license plate and a duration. So it can be emulated actually just by putting a JSON file into the storage. But I think it's gonna, well, then you can basically, imagine that this is the stream, and then you would just again read the stream and do the join, and you would have then a third stream that is a join of two streaming data. The thing is that I still didn't find a way, pragmatic way to, because then we need to look into the license plates are generated. So I don't have the emulator that generates these payments, but basically would have another stream that would be like this. For example, we can save it. Actually, the funny thing is that you can consider also a file system as a source for your streams. So it doesn't need to be Azure Event Hub. In that case is, I just stored this file, right? You see it here. Just imagine we would have it. So, and I can get it back. So if we do it without joins, you see, and I've got my, so that is already the stream, which is the source. There it was Event Hub, but here the source is just the file folder. And so if I put a new file here, that's what I thought kind of doing, right? So you can do it like this, and then this, and then I can still do it. And then if I do it this, right? You see, I didn't rerun this because, but I put two files in the file system. So usually this is a scenario by itself where you do all kinds of log analysis, for example, where someone is saving the log files, and then you can use that stream. You see, it got two. So if I put another one, whatever, and so I just write the file, right? Oh, I overwrote it. So that one should pick it up. Yeah, here we go. That is actually more convenient actually way to test this streaming. And then I can join this just by using join, but this license plate, I'm not going to get any outputs because those are not the ones that are generated. So that is basically this. So we covered, the interactive part. Well, I still made it a bit for the reference. The batch stuff, which is the SQL stuff, and the stream joins, which is actually also enables quite an interesting scenarios. And from there on, basically, I think we have a couple of minutes to Q&A session, or otherwise, I'm still here. We can perhaps have a more detailed look into something. So yeah, thank you very much. And if you have any questions, I think we have a couple of minutes.